Greetings. Welcome to today's class. Just to start the class with a quick recap of what we were doing. If you recall, we were looking at the state space realization, and we were looking at what is called as an equilibrium state, and we define a state x star as the equilibrium state for a dynamic system. If this system starts at x star, remains at x star, right, for all subsequent time in the absence of any external input slash disturbance. Okay, so that's when we call x star as an equilibrium state. So now, how do we calculate the equilibrium state given the state space representation? Suppose, let us say we have the single input, single output system, x dot equals AX plus BU, and we want to calculate the corresponding equilibrium state. Of course, there is no external input, right? So U of t is 0, and the state doesn't change from x star once it starts there. So x dot at x star will be equal to 0. So we just solve ax star to be equal to 0. So now the solution to this particular equation depends on the nature of the matrix A. So for linear systems, there are two possibilities. The first possibility is that we can have a unique equilibrium state when the matrix A is invertible. So we have a unique equilibrium state at x star equals 0. That is what is called as the origin. So typically in this line of study, when people use the word origin, right? So they are essentially referring to the equilibrium state at x star equals 0. So that is essentially the origin in the state space. Okay. So the second possibility is that we can have A to be singular, in which case we have an infinite set of equilibrium states which belong to what is called as the null space of the matrix A. So how do we define the null space of the matrix A? Null space of the matrix A is a set of all vectors B such that A times B is equal to 0. Okay. So this null space is a continuum of states, okay, and it is infinite in size. Okay, so that's when A is singular, we have an infinite set of equilibrium states. Okay, so that's where we stopped in the previous class. So now let's build on this, and then let's do a couple of examples which we posed at the end of the previous class to understand these concepts. Okay, so let's first look at the matrix A, which is A is equal to 1, 1, 3, and minus 2. We can immediately observe that this is non-singular. Okay, so we can see that its determinant is not 0. So this is a non-singular matrix. So then what happens? Let's try to find the equilibrium state. To find the equilibrium state, we solve Ax dot b equal to 0. Of course, this state matrix corresponds to a second order system. How do I know that it's a second order system? Because please recall that the state matrix is a n by n matrix, right? So where n is the order of the system. So that is why we know that this belongs to this state matrix belongs to a second order system. So if we have that, what happens? The state matrix is going to be 1, 3, 1, minus 2, and x star is going to be equal to x1 star, x2 star. Okay, that is going to be equal to 0 and 0. Okay, so immediately on solving these two equations, we can immediately see that x1 star has to be 0 and x2 star has to be 0. Okay, so that is the only possibility with this particular case. That you can easily establish by solving these two equations. Okay, and determining that both the equilibrium states x1 star or the components of the equilibrium state x1 star and x2 star have to be 0. Okay, so there is no other choice. Okay, so this implies that the equilibrium state x star is equal to 0. So what we have is that we have a unique equilibrium state at the origin. Okay, so that's what happens in this particular problem. I hope it is clear how we reach this conclusion, right? Of the equilibrium state being unique and being at the origin when the matrix A is invertible, right? So now going to the next example, in the second case, the what is it? The state matrix for the once again for the second order system is this, right? 1 minus 3 minus 2, 6. We can immediately see that this is singular, right? So if you calculate the determinant of the matrix A, it is going to be 0. And we can also see that the rows, the two rows are multiples of one another, right? So if you multiply the first row by minus 2, you get the second row. Similarly, if you multiply the first column by minus 3, you get the second column. So the rows are, what to say, not independent of one another, the rows and columns. Okay, so they are related by a constant factor, right? So consequently, the matrix A is singular. Then what happens, right? So let's find out how do we calculate the equilibrium state in this case. So once again, we calculate A x star to be equal to 0. So this will lead us to 1, minus 3, minus 2, 6, and then like x1 star, x2 star, that is equal to 0 and 0. So now if we solve these two equations, what are we going to get? We are going to get x1 star minus 3x2 star is equal to 0, and the second equation is minus 2x1 star plus 6x2 star is equal to 0. So you can immediately see that, the two equations are one and the same, right? So in fact, if you multiply the first equation by minus 2, you get the second equation, right? So consequently, these two equations imply that x1 star minus 3x2 star is equal to 0. There is only one equation in reality, right? But however, we realize that there are two unknowns, but one equation, right? So this is where things get interesting. So essentially, we can interpret that x1 star is going to be equal to 2x2 star, right? So consequently, let x2 star be some c, okay, where c is some real number. This implies that x1 star will become equal to 3 times c, okay. So consequently, the equilibrium state, which is x1 star, x2 star, can be written as c, 3c and c, okay. So where c is some real number, and this also people will rewrite this as x star to be equal to c times 3, 1, okay. That c is some real scale. Okay, so this is how we will get the equilibrium state in this example, right? I hope it's clear how we got this, right? Because we process Ax star to be equal to 0, but we can immediately recognize that we are essentially going to get only one equation, right? So both equations that we obtain by expanding Ax star equal to 0 reduce to the same equation, right? Reduce to a single equation, which then helps us in concluding that the equilibrium state is some scalar multiple of the vector 3, 1. Okay, so in fact, this is what is called as this in this particular example is the null space of A. So what is the null space of A? You multiply the vector by 3, 1, the matrix A by 3 and 1. You will see that you will get 0. All right. So you multiply the matrix A by any scalar multiple of the vector 3 and 1, you will see that the answer will be 0. So that is the null space of the matrix A. All right. So in this particular case, we observe that there is a continuum of equilibrium state. Okay, as we discussed previously. Why there is a continuum? Please note that the constant c is a real scalar, right? So that can go from minus infinity to plus infinity. So there is an infinite set of equilibrium states, Okay, but that's a continuum also. Why is a continuum? Because it's a continuous set, right? Because T is a continuous, what to say, set of real valued numbers, right? So it goes from minus infinity to plus infinity in a continuous range. So we get infinite equilibrium state, and that this set of equilibrium states is a continuum of equilibrium state, right? So I hope the terminology is clear now, right? Why we essentially call the why we have infinite set of equilibrium states, and why do we call this as a continuum of equilibrium state? Okay, when the matrix A is singular, right? So that is the result when the matrix A is singular. So in summary, for linear time invariant systems, when we talk about equilibrium state, there can be two sets of equilibrium states. Okay, so the first equilibrium state is essentially one wherein like we essentially have the matrix A to be invertible, and consequently x star equals 0 is the unique equilibrium state. In the second case, the matrix A is singular, and consequently x star is an infinite set of equilibrium states that belong to the null space of the matrix A. Okay, so these are the two results. And why are we talking about equilibrium states? Please note that when we are discussing about state space representation, once again we are entering into control design using state space method, right? So as we already know, when we design a controller, we are always interested in two aspects, right? Stability and performance. So stability, we were always looking at bounded input, bounded output stability till then. There is an alternate motion, which is the stability of an equilibrium state, and that's what we are pursuing now. All right. So I hope it is clear where we are and how we are proceeding. All right. Okay. So now, having looked at what to say linear systems, we are just going to take a small digression to nonlinear systems. So we are going to ask ourselves the question: what happens in the case of nonlinear systems? So if we have nonlinear systems, what happens as far as the equilibrium state of nonlinear systems are concerned, right? So, so essentially, in general, the state equation of nonlinear system can be written in this form. Okay, can be written x dot t is equal to some nonlinear function f, which is a function of the state and the input. Okay, so that's how it is written. All right. So if we have a nonlinear system, its governing equation, its state equation could be written as x dot equals some function f, which is nonlinear, okay, of the state x and the input u. All right. So if we want to essentially find the equilibrium state, once again, when we have x to be equal to x star, what happens? The input is 0, and x star is also equal to 0, right? So that's the definition of equilibrium state, right? So how do you define equilibrium state? Equilibrium state is the state at which the system would remain if there are no external inputs, right, or perturbations or disturbances provided to it. So consequently, the equilibrium state can be obtained by solving f of x star to be equal to 0, right? Because that's what we can immediately figure out, right? So if we substitute u of t to be equal to 0, and also x dot to be equal to 0, we are left with f of x star, right? And we essentially solve f of x star equal to 0 and we get the equilibrium, right? So to consider an example as far as this particular is concerned, as what is the case is concerned, let's take an example of a simple pendulum. Okay, very simple case. So let us say we have a massless thread to which we tie a mass m, all right, and what we do is that like this length of the arm, right, of this pendulum, let's say is L. What we do is that like we perturb this pendulum by an angle theta. This is a function of time and leave it. So this pendulum is going to keep on oscillating, right? So that's what is going to happen. So let us neglect friction for the time being, right? So the governing equation or the equation of motion of the simple pendulum okay, neglecting friction, of course, is given by, so how do we get the governing equation? So I'm going to leave this as an exercise to you. Okay, so please do it. If you have any questions, you can let me know in the next session. Okay, so one can obtain the governing equation in this form. All right. So this I leave it to you as an exercise to do. So this governing equation would be theta double dot p. It's a second order equation plus g by L sine theta t equals 0. Okay, so immediately we can see that this becomes a non-linear ODE because like sine theta is a non-linear function of theta. Okay, so that is why this is a non-linear system. Of course, for small theta, sine theta will become equal to theta, and consequently we will get what is called as a linearized system. But let's consider the non-linear system as it is, right? So, and then let's analyze what we get out of it, okay? So, but what I want you to do is essentially derive this equation of motion, right? So, that is for this system, the governing equation of motion is going to be theta double dot t plus g by L sine theta t equal to 0, okay? So, this is a second order system, by the way, all right? So now let's analyze this. Okay, so let's write the state space representation for the system. So let us choose the two state variables to be x1t to be equal to theta t and x2t to be theta dot t. Okay, so the process remains the same. Okay, so we need to choose as many state variables as the order of the system. Okay, so this is anyway a second order system. So we choose two state variables, right? The first state variable is the angular displacement theta, and the second variable, state variable, is the angular speed theta dot. So then what do we do to write the state equation? The process is the same once again. So what we do is that we take the first derivative of each state variable, right? So what happens? So if we take the first derivative of x1, we get x1 dot. X1 dot becomes equal to theta dot, which is nothing but x2, right? That is very simple, very straightforward. Now x2 dot is going to be equal to theta double dot t. That is going to be minus g by L sine theta t, right? How do we get this? From this governing equation, right? So we see that we use this equation here, right, to get the to substitute for theta double dot t, I guess as minus d by L sine theta. And since theta is x1, we can rewrite this equation as minus d by L sine of x1t. Okay, so that's what we have. All right. So these are the two state equations. Okay, so we can put them in the state space form by combining the state variables. So we have x1 dot t and x2 dot t as a state vector, as a column vector, right? Then what do we do? We, of course, now we can write it as ax. So what we do is that we write it as f of x. Okay, so this is going to be x2 of t. Then we will have minus d by l sine x1 t. All right. So this is a state equation in this particular case. Okay. So this is a state equation for this nonlinear system. So we can immediately see that this is a nonlinear equation because of the appearance of sine theta. So in the standard form, this is x dot. Okay. And this is f of x. In this particular case, there is no input as such. There is only a perturbation. Okay, we are only tapping the pendulum from its initial equilibrium state, and then like we are going to see what is going to happen to the pendulum. Okay, so now let's see what happens, right? So if we now want to look at the equilibrium state, right? So the equilibrium state x star can be obtained using, like f of x star to be equal to 0. Okay, can be obtained by solving f of x star to be equal to 0. Okay, so that's what happens. All right. So what do we have? We essentially solve this equation. So f of x star is x2 star, and then minus d by l sine x1 star equal to 0 and 0. Okay, so immediately what do we get? From the first equation, we get x2 star to be equal to 0. From the second equation, we get minus d by l sine x1 star to be equal to 0, which implies that sine of x1 star equal to 0. So from trigonometry, now we know that x1 star will be equal to from n times pi. N will be 0, 1, 2, etc. Right? But as far as the physical problem is concerned, x1 star can be only 0 or pi. Okay, for the pendulum, because it can be either vertically down, which in this case, which corresponds to n equals 0, or it can be vertically upwards, right? So we can hold or we can have a pendulum vertically upwards, right? So that will correspond to n equals 1. So on the other hand, if we have n equals 2, we come back to the vertically downward position once again, right? So if I have to illustrate this, so n equals 0 will correspond to the vertically downward position, right, where theta star is 0, right? So this is where x1 star is equal to 0. Vertically upward position is a case where, let's say, the pendulum is like this, right? x1 star is equal to pi, okay, 180 degree or pi. In both cases, what to say, x2 star is 0, so x1 star, x star can be written as 0, 0 in this case, sorry. Okay, the equilibrium state vector x2 star, x star in this case can be written as pi and 0, right? So now we have a, what to say, unique proposition, right, or a unique case, right? So in this particular case, the equilibrium state is not unique, okay, certainly, but neither is it an infinite set, right? It is a finite set with a space, what to say, with a gap in between, right? So this is unique to nonlinear systems, and this scenario, which happens with nonlinear systems alone, uh, is corresponding to what is called as the presence of multiple isolated equilibrium states. So what do we mean by multiple isolated equilibrium states? That is, we have more than one equilibrium state, okay, as we have seen in this particular example. Okay, we have two equilibrium states, 0, 0 and pi 0. All right. And now the question is, it's not unique, but neither is it infinite. right? So previously we saw two possibilities of equilibrium states, right? For linear systems, that is, we had a unique equilibrium state at the origin, or we had an infinity of the equilibrium state, right? A continuum of equilibrium. So for nonlinear systems, in addition to the two previous scenarios, right, we have the third case, which is not true for linear systems, which is not applicable for linear systems. So for nonlinear systems, we have a third scenario where we can have a set of multiple isolated equilibrium states. All right. So that is what I say, a unique proposition with nonlinear. Okay. So now, if we look at this nonlinear system as an example, right? What can we immediately tell? Like, because we can immediately say that, going back to the example of the simple pendulum, we can immediately say that, look, if I tap this pendulum, right, it's going to oscillate around the equilibrium state, right? So intuitively we'll say this is stable, right? This scenario is stable, right? Because we are talking at an intuitive level, right? We tap the pendulum, it is going to remain around the equilibrium state, right? It is going to oscillate around the equilibrium state. So we will say, hey, this scenario is stable. On the other hand, if we tap this will fall down, right? It will become like this. So we will intuitively call this as an unstable state, right? Or an unstable equilibrium state. Okay. So we can observe that this motivates us to come up with definitions for the notion of what is called as stability of an equilibrium state, okay, which we will subsequently are going to do. Okay, so so ultimately, like from big picture perspective, like we can see where we are headed, right? So we are going to look at control design using state space representation. So we have started looking at notions of stability. So we have already learned about bounded input, bounded output stability. Now we are looking at stability of an equilibrium state. Before we go to stability of an equilibrium state, we need to first define what is called as an equilibrium state. So we defined that that is an equilibrium state is one where the system will continue to remain as long as there is no external input, right, or perturbation or disturbance. So that is an equilibrium state. So we saw how to get the equilibrium state from the dynamic equation and what happens with linear and non-linear systems. Okay. So to summarize, uh, what we have learned, if you look at equilibrium, the concept of equilibrium state, we can have unique equilibrium. Okay. We can have continuum of equilibrium state. Okay. Or we can have multiple isolated equilibrium. Alright. So the first two are applicable for linear systems. Okay, for linear systems, we can have only these two. That is, either the equilibrium state has to be unique or it has to be infinite and a continuum of equilibrium state. Okay, so those are the two scenarios that can that are possible for linear systems. However, for non-linear systems, we have a third scenario which is also possible, which is the scenario of multiple isolated equilibrium. Okay, so this is possible only for non-linear. Okay, so I hope these concepts are clear. All right. What we are going to do is that, like, we are what to say, going to discuss about the notion of stability of an equilibrium state in the next class. Okay, and then we'll see how do we then come up with then criteria, for evaluating the stability of an equilibrium state using the state space representation. Okay, so that's something which we are going to look at in the next session. In the time remaining in this session, I'm going to discuss the midterm exam and its solution. So that is why I'm going to continue with the discussion on stability of equilibrium state in the next. Okay. Do you have any questions about what we have learned about equilibrium states today? Okay. So if not, let me go and discuss the solution to the midterm exam questions. Okay. So let me discuss the key. Of course, the midterm exam, as we discussed, was based only on classical control, and we had problems from the related concepts. So let me just discuss the answers, and if you have any questions, you can also write. Okay? So the first question is, I had given this mass spring damper system, which was where there was a non-linear spring. So, however, the system parameters MCK are constant; they are not functions of time. So this is a non-linear time varying. Okay, sorry, non-linear time invariant system. Sorry about that. So the correct choice is choice A. Okay, so that is the reason. And if you look at the second problem, we had we have been given the transfer function. Sorry, not the transfer function. The function in the S domain as we have 4 divided by S squared plus 4. Please note that Laplace of sine 2t is 2 divided by S squared plus 4. So there's an extra factor of 2 in the numerator. So the answer is 2 sine 2t. So the correct choice is C. So the settling, third question is about settling time of the first order system. Please note that we need to put it in the standard form. So what is the standard form? It is P y dot C plus y equals U. So, but that is not in the the equation is not in the standard form. So we need to divide by 2, and then we get the time constant as 0.5 seconds. And we know that the settling time is 4 times the time constant. So consequently, the answer is 2 seconds. Okay, so the correct answer is choice C. And as we have learned that the damping ratio of a critically damped second order system is 1. So that is the answer to question number 4. So if we look at question number 5, based on the structure of the transfer function, an integral controller will have a structure of Ki by S, right? So consequently, that would introduce a pole of an open loop pole of the origin. So the correct answer is choice C. Then moving on to question number 6. Of course, here, in fact, by a strange choice of numbers, like what happened was that I choose the pole also to be at -1. So in this case, there is a pole zero cancellation. So I accepted alternative answers also. So as long as you provided the reason, but the thought process was that like n equals 2 and m equals 1. So the number of asymptotes is equal to n minus m, right? As we have learned. So the number of asymptotes is 1. So the answer will be, so that is the answer to question number 6. So for question number 7, we are given the open loop transfer function. We need to calculate the gain crossover frequency. So what we do is that like we solve for the magnitude of gj omega g hj omega g equal to 1, and then we get the answer to be 0.486 radians per second. Okay, so that is choice B. And for the same open loop transfer function, the phase crossover frequency is infinity, right? So because the phase of the open loop transfer function is minus 90 degrees minus tan inverse of 0.5 omega, and we can observe that this will tend to minus 180 degrees only when omega tends to infinity. So that's why the phase crossover frequency tends to infinity for this false. Okay, going on to question number 9. The Planck transfer function is 1 by s plus 2. Please note that we need to put it in the standard form, 1 by ts plus 1, right? So if you put in that form, capital T comes to be 0.5, but the corner frequency is 1 by t, right? So that becomes 2. So the answer is choice B. Okay. Question number 10. Once again, we need to find the closed loop transfer function, and if you look at the closed loop characteristic polynomial, which is s squared plus 2s plus kt minus 3. So that's the second order polynomial. So consequently, the necessary and sufficient condition for closed loop stability is that all coefficients must be non-zero and of the same sign. So Kt minus 3 should be greater than 0. So Kt is greater than 3 is the correct answer. That is choice C. So question number 11, if you look at the Planck transfer function, it is 1 by s cubed plus 2s squared. By looking at the structure of the Planck transfer function, the fact that we are given a unity feedback, you can try it out. If you try each controller, you will find that in many cases, the closed loop characteristic polynomial will miss the term, right? Either the f term or some other term. So only a PD controller will be able to stabilize the system. Okay, so that is the correct answer. So it is choice C. And question number 12.
Sir, can I ask one question about the ninth problem?
Yes, please.
So in the ninth. Okay, this is what I have done, but I just had one question. So in this case, we have two, right? One is just the magnitude 0.5, and another is 1 by ts plus 1, right? So there are two, and when we combine them and plot them, the corner frequency is gonna increase by the same magnitude, right?
No, the corner frequency doesn't change, right? So because what will happen is that the factor of 1 by 2 will only shift the magnitude curve of 1 by 0.5 s plus 1 either in this case down, right? Because 1 by 2 is a 0.5, right? Yeah. So the magnitude will be 20 log of 0.5, which will be a negative number, right? So, but what is the definition of the corner frequency? It is the frequency. It is a frequency.
The intersection of
the low frequency asymptote and the high frequency asymptote will intersect, right? So that is not changed by the factor of 1 by 2. Okay.
Got it. Sir.
Okay. Yeah. So because 1 by 2 is only going to shift the entire magnitude curve down by 20 log.
Exactly. So that's what was my question. So if since my system is combined system and if the entire thing is getting shifted, so okay, I got my answer. So even in that case, I'm gonna consider only the parameter which has a corner frequency.
Yes. So the scalar, the constant scalar doesn't affect the corner frequency, right? It will affect the value of the low frequency asymptote. The low frequency asymptote will no longer be 0 decibel, right? Yeah. But the corner frequency will remain the same.
Okay, sir. Thank you.
Okay. Sure. Yeah. So I think moving on to question number 12. The unit step response of the standard first order system is 1 minus e power minus t by capital T. So at time instant which is equal to twice the time constant, we will get the answer as 0.86. Okay, so that's what will happen. Then question number 13, you can do it in multiple ways. Of course, I use the final value theorem, and we can get the answer as 1 by 2, right? So you can also take the inverse Laplace transform and do the partial fraction expansion and get the answer to be 1 by 2. Okay, question number 14. The Planck transfer function is 1 by s squared plus 4s. Please note that can be factored as 1 by s times s plus 4. So consequently, the output is going to be unbounded only for a step input, right? So that is the answer to question number 14. So for question number 15, once again we just apply the Routh criteria, and we get the answer to be choice C. Okay, so that is for the range of k between 6 and 2, the closed loop system stable. All right. For question number 16, please note that this is a case where k is given to be negative. So what we need to do, we need to substitute k hat to be minus k and follow the second set of steps, right? That is what we learned for negative feedback, positive feedback with positive k, right, or positive k hat. So if you do this, the root locus will be as shown here. So consequently, the correct statement will be point A and B. Okay, choices A and B in the question. So even if you have got one of the two correctly, I've given you half the mark. Okay. That is how I have graded them. So question 17 to 19, I have given the peak time and rise time of a standard second order underdamped system. The main step here is that you need to convert beta from radians to degrees. Okay, so that is an important step. So I think if you do that properly, you will get these answers, right? So for the damping ratio, we will get it as 0.707, which is choice B in question 17. The maximum peak overshoot will be 4.3%, which is choice A in 18. And the settling time will be 1.33 seconds, which is choice B for question number 19. Okay. Yeah. Question 20 and 21, once again, what we need to do is that we need to calculate the open loop transfer function and get the static question error constant. One main thing is that the steady state error to the unit step input is 1 divided by 1 plus kp. Okay, not 1 by k. Okay, so that's a critical step. So if you do that, we will get the answer to be 1 by 3, which will be choice D for 20, question 20. And in question 21, what I told is that now let's say we have the the controller transfer function to be 4s plus k, right? Then we wanted the steady state error to be less than 0.1, the magnitude, right? So to solve this inequality, we'll get k to be greater than 9, which will be choice A for question number 21. Okay. Then going forward to question 22 and 23, in 22, I had given the open loop transfer function as x plus 2 divided by s squared plus 4s. So we can immediately see that we can decompose this transfer function into 4 blocks: 0.5, 1 by s, 0.5 s plus 1, and 1 divided by 0.25 s plus 1, right? So due to the presence of the 1 by s term, we will see that the low frequency asymptotes will have a slope of minus 20 decibels per decade, right? So that is the answer to question number 22, which will be choice B. Okay, yeah. Yeah, any question about this one, problem? Hello? Ramkumar, you are unmuted. Do you have a question? Hello, can the others hear me?
Yes, sir, we can hear you.
All right, okay, great. Ramkumar, you are unmuted. Do you have a question? Okay, so let's go ahead. So we can observe that there's a 1 by s term. So consequently, the slope of the low frequency asymptote will be minus 20 decibels per second. And as the frequency tends to 0, once again the phase will tend to minus 90, right? Because we have a 1 by s term, whose phase is constant at minus 90 for all frequencies, right? So that is why we have the answers to be the corresponding choices. All right? Yeah. Now moving to questions 24 and 25. So we want to evaluate the closed loop transfer function, and using the Rouse criteria, we can immediately observe that the closed loop system is stable for all k greater than 0. And if you want distinct real closed loop poles, if you look at the closed loop characteristic equation s squared plus kx plus 9, we calculate its discriminant, right? B squared minus 4ac, that should be positive. So using that criteria, we will have k to be greater than 6, right? And that will give us distinct real closed loop poles in the left of component. Okay, so the answer is choice B, okay, for question number 27. Okay, so these are the answers to the midterm exam questions. Are there any queries, points for discussion about these questions? Okay, so if there are no questions about the midterm exam, I will close today's session here. And then we will continue our discussion on equilibrium state and stability of an equilibrium state in the next class. Okay, thank you.
Professor, actually, one question regarding project 1.